Welcome to Chemical Reactions Part 5. In this video, we're going to look at chemical equilibrium and Le Chatelier's principle. This is very important because as a biological system, we're in constant equilibrium and our equilibrium changes, and so this will be an essential topic for understanding our health and how chemistry plays a role. Let's get started. All right, so equilibrium is a term when the forward and reverse reactions proceed at the same rate, right? Then the concentration of reactants and products will no longer change and the reaction has reached a state of equilibrium. Okay, so before this chapter, we were just looking at reaction arrows where we said that it went from the reactants to the products, and we would just say that it's like all 100% complete. Okay, and many reactions are like that. But these reactions are both the forward and the reverse reaction can occur, right? So we can have a mix of reactants and products simultaneously because our forward reaction is occurring at the same rate as the reverse reaction when we're at equilibrium. Okay, so let's focus on equilibrium first, and then we'll look at what happens when we disrupt equilibrium. Okay, so we will start with a really simple reaction. We'll just take this compound HA, and it's going to dissociate into H plus and A minus. This is actually a weak acid, and we'll study that in the future, so don't worry about the acid part right now. Just focus on the equilibrium, all right? So what happens, right? So initially, let's say we have 100% of HA, okay? And so we have we'll make a graph here. All right, so for the forward reaction, we'll use a green arrow, and for the reverse reaction, we'll use a red arrow. Now, we're going to look right here, right? So this will be our reaction rate on the y-axis, and then this will be time on the x-axis. And so what happens is initially all we have is HA, so it dissociates, and so it has a very high rate, but then as the concentration decreases, the rate lowers. And so then this right here, right, this is going to be when we're at equilibrium. And the reason why is because initially there is no reverse reaction because there are no products. But once HA starts to dissociate, then H plus and A minus will reform. And so then we'll start to get our reverse reaction. And there we go. And so right here at this time, we see that the forward and reverse are at the same reaction rate. And so then this would be, right, where the reaction reached equilibrium. Okay, so it didn't start in equilibrium. So we just started with pure HA. It started to dissociate. And then as the H plus and A minus formed, they wanted to reconnect. And so here we've reached equilibrium. Okay, so now we'll try to line up this next graph the same. Okay, so that's our reaction rates. So the reaction rates are the same at equilibrium. Now let's look at the reactant and product concentration. Okay, so we'll keep HA as green. There we go with our forward reaction. Okay, and I'm going to try to line this up so we have it all happening together. So we'll go here. Alrighty. So now along our y-axis we'll have the concentration, right, of the reactant or product, whatever we're looking at. So here we're going to look at the reactant. And so then what we'll see is that since we started with pure, oops, I'm sorry, I lost the page. Since we started with pure HA, the concentration was high, and then it decreases And then when we reach equilibrium, it remains unchanged. And then at the same time, we have the A plus and the A minus, right? So initially there wasn't very much, but then as the reaction proceeds, there we go. So then this flattens out. So here we are at equilibrium, right? At equilibrium. So at equilibrium, the rates of the forward and reverse reactions are the same, and the concentration of reactants remains constant, and the concentration of the products is no longer changing. So this red line here should be nice and flat. Okay. So if we look at this, all right, so we have to understand equilibrium. Okay. So is the concentration, let's make sure, right? So this was the products, right? And this was our reactants. So this is a common misconception. Is the concentration of products equal to the concentration of the reactants at equilibrium? No, right? So what we can say is that the concentration of reactants and the concentrations of products remain constant. Oops. At equilibrium. Okay. All right. The forward and reverse rates are equal, but the concentrations of products and reactants can be different. They just don't change. So, at equilibrium, have the reaction stopped? No. Right? Because these concentrations are remaining the same, it gives the illusion that the reactions have stopped, but that's not the case. Okay, so now let's dig a little bit deeper into equilibrium. Okay, so it's often called dynamic equilibrium, right? Because of the reaction rates, right? It's a dynamic equilibrium because the forward reaction, right? The forward and reverse reactions continue to occur. Okay, so that the unchanging concentrations of products and reactions is an illusion that there's nothing happening, right? So on the surface it looks like nothing's happening, but inside the forward and reverse reactions are happening. Okay, so now let us integrate everything that we've learned about reactions to date. All right, so we're going to do a reaction energy diagram. So I'll give us some space for that. So for our reaction energy diagrams, right, we're going to have energy on our y-axis, and we'll put time on our x-axis. Okay, and so what type of curve? All right, so we're going to do exothermic, right? They're considered spontaneous because the products are more stable than the reactants. All right, but spontaneous does not necessarily mean fast. All right, so let's do this. So we'll put exothermic. So our products are lower, more stable, lower in energy than our reactants. And of course, if I gave you an actual reaction, you'd show the chemical formulas. Okay, and exothermic means, right, that this energy is going to be released. So we put minus delta H, right, or delta H less than 0. Two ways to show that. Right, then right here, right, here's our activation energy, our E sub A. So the reactants need to get up to, what's this called up here, right? This is the transition state. So remember from collision theory, right, that the reactants have to collide with a minimum collision energy, right, the E sub A, the activation energy, for a reaction to occur. And not only do they have to have this minimum collision energy, but they need to have the correct orientation. Okay. So then, right, so this is it's exothermic. It's considered spontaneous, but it's not necessarily fast because it has a large activation energy. And so then we've learned that we can add a substance called a catalyst. And what the catalyst does, right, so now with the catalyst, we can lower the transition state energy, right, which lowers the activation energy, which gives us the faster reaction rate. Okay, so now let's move forward. Had a little review, tying this all together. And so the main thing here with equilibrium, right, especially if we have a low activation energy, is we can have the forward and the reverse reactions happening simultaneously. All right, so now let's go. We understand a system at equilibrium. Now comes the more interesting thing, changing equilibrium, because our body wants us to be in equilibrium, and then we're doing things to throw it out of equilibrium. We're exercising, we're eating, we're drinking water, we're doing all kinds of things. All right, so a gentleman by the name of Chatelier, he came up with this principle that if we start with a system at equilibrium and we add stress, we apply stress to the system, the equilibrium is going to shift to relieve the stress. Okay, so keep in mind, right, that reactants are on the left and products are on the right. Okay, so we're going to talk about things going to the left or the right, and just remember that that's referring to the reactants in the products. Okay, so you know, humans, we know a lot about what human stress is like. What causes stress in a chemical equilibrium situation? Well, if we change the amount, right, the concentration, amount or concentration, we use those square brackets for concentration, right, of reactant, right, or product, that's going to create stress, right? If we change the temperature, that will create stress. Or we can change the pressure or volume of a system, and that will create stress. Now with pressure and volume, the important thing to note, this is for gas phase materials, reactants and products only, gas phase only. So we only worry about the effects of pressure and volume when we have gas phase reactants or products. Okay, so when we're doing the stress, we can think about it, right? So here's our system at equilibrium, right? So we can increase, right, or decrease things. And what does that do to our balance, right? It shifts our balance to the right, right? So if we cause stress that raises, right, increases something on the reactant side or decreases on the product side, we say we're shifting the equilibrium to the right. Okay, we can also shift to the left, but I just wanted to give you a little warm-up before we get started. All right, so now we're going to look at an actual chemical reaction. All right, so here we are at equilibrium. So the phosphorus trichloride and chlorine are reacting to produce the phosphorus pentachloride and some heat. So this is the equilibrium, and we start, it's at equilibrium, right? So at equilibrium, the forward reaction rate is equal to the backward reaction rate, and all of the concentrations are remaining constant. But notice they're not equal to each other, right? Okay, so now what we're going to do, now we add the stress, okay? So here is the stress. We're going to add the chlorine, all right? So here's the stress. Okay, So what did we do? We increased the chlorine concentration. So here's our teeter-totter, right? The chlorine is over here on the reactant side, right? And what did we do? We increased it. We made it go up, right? Increasing is going up. So what have we done to our teeter-totter, or to our balance, right? We've shifted it, right? So if we add the chlorine, we are going to shift the equilibrium, right, to the right, right, to the product side. Okay, so now the system has reached a new equilibrium. All right, so in theory, right, if we put the stress, we added stress on the left, it pushed the reaction to the right, so we would expect to have, now we would expect to have more product. Let's look and see. And we would expect to have less reactants. So let's check this out. Okay, so at the new equilibrium, we compare, right, so we had the original equilibrium, we added the stress, and now equilibrium has been restored. Okay, so at the new equilibrium, what happened to the phosphorus trichloride, right? The concentration of the phosphorus trichloride, right, it decreased. What happened to the chlorine, right? Well, it went from 10 to 8. The concentration of the chlorine decreased too. And then our product, right, it went from 5 to 6. So the concentration of our product increased, okay? So when we say that we've shifted the equilibrium to the right, it means that the reactants are going to react with each other to produce more products. So which way did the equilibrium shift? To the right. Okay, so now let's try a different one. Okay, so we start with our reaction at equilibrium, and now we're going to decrease the phosphorus trichloride. Okay, so the phosphorus trichloride, it's on the reactant side. Okay, so we always look to our reaction to figure out what side to put the substance in question. And now we're going to decrease it, right? So decreasing, we're going to go down. So if we decrease, then that's going to cause our balance, right, our teeter-totter to shift to the left. Alrighty, so we would say that we have shifted the equilibrium to the left, right, which is the reactant side. Okay, alrighty, let's keep going because we talked about there being more ways to stress a reaction. So we've looked at changing concentrations of reactant or product. Now we're going to look on the next pages at what happens when we change temperature, pressure, or volume. So let's bring in the next page. So we'll just keep with the same reaction so we don't have to worry about any of that. All right. So with temperature, right, this is where we're going to take advantage of understanding whether the reaction is endothermic or exothermic, okay? So here, heat is a product, so we would describe this reaction, right, as exothermic, right? So the value of delta H, positive or negative, right? So that means delta H is negative, right, which means it's less than 0. Okay. Alrighty, so now if we look at our reaction in equilibrium, right, heat is on the right, so we're going to put heat over here on the right. And so now if we increase the temperature, right, that means we're going to go up on this side. So if we push up on the right side, right, we're going to shift our equilibrium, right, shift to the left. Okay, so we can see that if we increase the temperature, it favors the reverse reaction. And I've already answered this one. If we increase the temperature, right, the equilibrium shifts to the left. All right. Oh, okay, right? So if we increase the temperature, what are we doing here? I missed this part, right? So if we increase the temperature, we're definitely adding heat, right? So that's why we did that. Okay. So then, if we decrease the temperature, right? So heat, this is an exothermic reaction. Heat's on the product side. Now, if we decrease the temperature, right, we're going to pull down here. So we're going to shift the equilibrium right. Okay. So decreasing the temperature is actually going to favor the forward reaction. All right. So if we decrease the temperature, we shift to the right, and this is going to favor products. So another part of the videos is just kind of making sure that we can talk about this and with a variety of terms, and we can ask questions in a variety of ways. And so we want to make sure we don't get thrown off by how the question is asked. Okay, so if we were going to do a reaction energy diagram for this reaction, right, so now we'll put in a little more detail than our previous one because now we have an actual chemical species to talk about, right? So it's still exothermic. So the phosphorus pentachloride is lower in energy than the phosphorus trichloride and the chlorine, right? And so then here's that heat released, right? The minus delta H, there's that heat released because it's exothermic. And then, of course, we would want to put in our activation energy and the transition state. Okay, so we're bringing it all together. So we've looked at the effects of concentration, we've looked at the effects of temperature, and now we are going to look more closely at the change of pressure and volume. Okay. So, here we go. Voila. All right. So now, when we are changing pressure, remember that we only look pressure and volume, right? Only look at gases. All right. So, when we look here, we see that we have 1 mole of phosphorus trichloride reacting with 1 mole of chlorine. They're both in the gas phase. So we see that we have 2 moles of gas on the reactant side. And when we look on the product side, we only see 1 mole of gas. Okay, so I noticed this pattern. So this is a Bennetism. I haven't seen it anywhere else, but it's pretty helpful. So basically what happens then is, I want to make sure this is right. Yeah. Okay, so basically we need to balance out the volume. All right, so if we have 2 moles of gas here and we only have 1 mole of gas here, we can put a V here for volume. Okay, now from gas laws, if we look at Boyle's law, right, we know that P1 V1 equals P2 V2. So what that tells us is if we increase the pressure, we're decreasing the volume, or vice versa. If we decrease the pressure, we're increasing the volume. So there's a relationship between pressure and volume that we have to bring to applying Le Chatelier's principle to gas phase reactions where we change pressure and volume. So that's why we talk about these together, because they're linked by Boyle's law. Okay, so if we look here, right, so how many moles of gas are present as reactant? We've already answered that, 2 moles. How many moles of gas are present as product? Only 1 mole. Okay, so if we look here, all right, so if we're increasing the pressure, right, then that means that we're decreasing the volume. So notice that the V is on the right. All right, so if we increase the pressure, then we're decreasing the volume, and so that is driving our reaction to the right, right? So it shifts the equilibrium to the right. Okay, and so let's think about this physically, right? So in the reactant side, we have 2 moles of gas clamoring for space, and on the right side, we only have 1 mole of gas wanting space, all right? So as we increase the pressure, we're squeezing, right? So we're squeezing the space, and so the reaction wants to have less moles of gas. All right, so as we increase the pressure, we decrease the volume, and that creates stress for the side with more moles of gas. Okay, and so from Le Chatelier, it says that the reaction wants to relieve that stress. So it goes to where, we don't need as much space. That's smaller volumes, okay? We don't need as much space. Okay, let's look at another reaction. What would happen if we change the pressure of this reaction? Would there be any effect? Let's look. Right, so we have 1 mole and 1 mole, so we would have 2 moles of gas on the reactant side. And with our coefficient here, we have 2 moles of gas on the product side, right? So if we change the pressure or the volume, right? So changing pressure or changing volume, right? Delta for change. Changing pressure or volume has no effect, right? Because the same number of moles of gas are on each side. Okay, so the other thing to keep in mind is that these are all potential sources of stress within a reaction, but they don't necessarily are relevant to every reaction we study, okay? So let's look at our last page here and tie in one last thing. We've talked about catalysts. So taking into consideration everything that we know about reactions so far, is a catalyst going to change the position of the equilibrium? No, right? What does a catalyst change? The catalyst right? The catalyst decreases the activation energy, which increases the reaction rate. So basically, what a catalyst does is it lets the reaction get to equilibrium faster, but it doesn't change the position of equilibrium. Right? So it allows equilibrium to be reached more quickly, faster. Okay, but it doesn't change the destination. It's like putting in the expressway, right? And so we've just talked about this, right? So here would be our normal reaction. Here, energy on the y, time on the x, right? Here's without catalyst. Okay, and then if we add the catalyst with catalyst. Okay, so here, right, there's our minus delta H. Okay, this energy difference between reactants and products, right, this determines the equilibrium. Okay, so the relative energy of the reactants and products, is going to determine our equilibrium. And remember that the catalyst or the activation energy just says how fast it takes. So it's important, everything's related, but it's important to know the boundaries. Okay, and then just to kind of come full circle, all right, so these are the reaction energy diagrams the way we're used to seeing them. And then to follow through, right, if we have, here's our reaction rate. Okay, and so if we don't have a catalyst, we have our forward and our reverse reactions. Okay, and we get to equilibrium. Right, here's time. Okay, then if we add the catalyst, right, with the catalyst, then here we go. Notice, see, we're getting to the same place, right? We just get, right? So with catalyst, equilibrium is reached faster. Okay, so at this point, we've pretty much covered everything we need to know about the energetics of reactions. So this would be a good time to review these notes, make sure you feel really solid on the concepts, find a few practice problems in your textbook, and be ready for class. I'll look forward to seeing you.